think we just do minus 1 and minus 6, right? Because then we get a minus 1, minus 6 is minus 7, and we get the plus 6. So that shows me x equals to 1, or x equals to 6, right? But then this is one of these problems we need to check if they're extraneous or not, right? So plug in 1, does it work? Is 1 equal to question mark 3 plus the square root of 1 plus 3? In other words, is it equal to 5? No, right? Is 6 equal to 3 plus the square root of 6 plus 3? Which is, by the way, 3 plus 3. Yes. So answer, extraneous. So finally, I just want to briefly review for you guys the problem of factoring quadratics. Right? How do we know whether or not we can factor a quadratic polynomial? What are the methods that we've used? Principal among them, of course, is just plain old factoring. But I'll just remind you the big story. The story is this: if we have ax squared plus bx plus c, right? Then this is equal to, well, like a times x minus r1 times x minus r2 for b squared minus 4ac greater than 0. It's equal to a times x minus r squared for b squared minus 4ac equal to 0. And it's equal to, well, let's just say it's irreducible over r for b squared minus 4ac less than 0, right? If b squared minus 4ac is less than 0, then x equals to minus b plus or minus the square root of b squared minus 4ac over 2a are complex roots. They're complex numbers. And if, we call these, let's say alpha plus or minus I beta, then ax squared plus bx plus c is equal to a times x minus alpha minus I beta times x minus alpha plus I beta. That's how it works. And when you multiply that out, that is x minus alpha squared plus beta squared. This is the theory in a nutshell. This is what happens. If the discriminant is negative, it factors over the complexes, but it can't over the reals. The quick way to the quick way to see these things for specific examples is to complete the square. So I'll give you an example. If we have, x squared plus 4x plus 5, all right, so to complete the square here, what I do is I take half of that, which is 2, right? I do x plus 2 squared. So I took half of 4, which is 2, and now I have to subtract 2 squared. And I add it to 5. So this is giving me x plus 2 squared plus 1. So if after completing the square you get a sum of a square and a positive term, that means it cannot be factored over the reals. If you want to, we could look at the discriminant in this case. What's a, b, c here? A equals 1, b equals 4, c equals 5. So b squared minus 4ac is 16 minus 4 times 1 times 5. That's 16 minus 20, which is minus 4. It's less than 0. you see we're in the irreducible case. This is important because if you're trying to decide if you factored completely, you need to recognize your foe, right? If you're up against an irreducible quadratic, you're done. You can't factor more. Like if I say factor x squared plus 4x plus 5 completely over the reals, the answer is, okay, it's x squared plus 4x plus 5. This is already factored completely over the reals. You can't break it down further. To break it down further, you need complex numbers. It's this. All right, that would be how to factor it over the complex numbers. All right. Now, I mentioned to you guys earlier that completing the square is what? It is a general method. It like always works. Factoring you may or may not be able to see. Completing the square we can always do. All right, so let's complete the square on this. This one's going to be a pain. I want to do at least one ugly problem for you today. This is ugly. Ugly. So if there's a 2 out front, or some other number out front, my first move is to factor that out. So I've got fractions we're going to have to deal with. 17 over 2. All right? But once you get to that point, then past this point, everything proceeds like it did before. So we take half of 5. So that's 5 halves. We square that. X plus 5 over 2 squared. By doing that, I return the x squared and the 5x term, but I'm also adding 5 over 2 quantity squared. So what I have to do, to be fair, is to subtract 5 over 2 squared. We've still got the 17 over 2 over there. All right? And so this is 2x plus 5 over 2 squared. And let's see here. So that is 25 over 4, right? And plus, what's 2 times 17? It's 34, right? 34 over 4. So which one won? The minus 25 or the plus 34? Looks like the plus 34 one, right? We've got 2 times x plus 5 over 2 squared plus 9 over 4, yeah? So is this quadratic completely factored over the reals? It is. That's right. It already was at the start because when we complete the square, we get plus, which means we're in case 3. If you were to check the discriminant here, which would have been way easier than doing all this, right? B squared minus 4ac is what? It is 10 squared minus 4 times 2 times 17, which is 100, minus 8 times 17, which is 136, I don't know. Could be wrong about that. What's 80 plus 56? Yeah, 136, I think it's, so anyway, it's minus 36. It's less than 0, which implies irreducible. However, look, completing the square is not without merit. What if you ask a separate question? What are the complex solutions? If I set this equal to 0, what are the solutions? The solutions are, well, x plus 5 over 2 squared, right, equal to minus 9 over 4. So if I take the square root of that, I get x plus 5 over 2 is equal to plus or minus the square root of minus 9 over 4. Well, that is plus or minus I times 3 over 2. So we get x is equal to minus 5 halves plus or minus 3i over 2. There you go. Those are the complex solutions to that equation. So there is a little bit of complex stuff on your final. Not a lot. Like maybe 2% of your final is complex. But so there might be like one question asking you for complex factoring in the complex solution, but the rest will be factor completely over the reals. So that's why I try to focus on that. Yeah. So if you're ever, my larger point to you is if you're stuck on factoring, you should be able to fall back on completing the square as a way to go through it. See, because whenever we can always complete the square. It's an algorithm. You take half of the middle term, square it, subtract the thing, go through it. Everything that we factored today, we could have used completing the square to factor. One final example of that. I would encourage you to write that stuff on your formula sheet and think about it. But one final example here. If I have x squared plus 4x plus 3, and I complete the square, I have x plus 2 squared, right? Minus 2 squared plus 3, which is what? X plus 2 squared minus 4 plus 3, which is minus 1. So if that happens when you complete the square, what's that mean? That means that you can factor it over the reals, right, if it's a minus. And in fact, then it's the difference of squares formula, right? Which in this case is x plus 2 plus 1, x plus 2 minus 1, which of course is going to give us x plus 3 times x plus 1, which is completely unsurprising because I hope most of you didn't need completing the square to factor this, right? You could just factor x squared plus 4x plus 3 as x plus 3 times x plus 1. But if you, for some reason, had a mental block on that, you could fall back on completing the square as a way to do it. Anyway, I try to preach this, but people are unwilling. But anyway, it's time to go.